Welcome to Bright Ray Academy, where the future of radiology students will be as bright as rays. All right, let's jump straight into it. Today, we're tearing down the literal walls of a piece of equipment that is, well, the absolute heart of medical imaging, the X-ray tube. In this explainer, we're going to strip away that heavy, clunky outer casing and dive right into the invisible, super dynamic core of radiologic science. We're breaking down exactly how this incredible piece of tech works, from the outside all the way in.
And yeah, that intro right there is our official mandate for today. We're absolutely bringing that exact academic, yet super inviting energy as we master the tech that actually makes diagnostic imaging possible. Let's get to it.
Okay, here's our roadmap for today. We'll hit Section 1, External Components, 2, Internal Components, 3, X-ray tube failure, and wrap up with 4, rating charts. Let's move. Section 1, External Components. Let's start with the macro view.
So think about this for a second. The tube and its housing are seriously heavy, right? They absolutely require a massive, robust support system just to safely move them around. The one you'll interact with most often is the ceiling support system. It's got this awesome telescoping column attached to perpendicular rails up top, which lets you perfectly dial in your source-to-image receptor distance, or SID. And you know that satisfying feeling when it's perfectly centered at the standard distance and just clicks into place? Yeah. That's what we call the preferred D10 position. We also have the floor-to-ceiling support setup, which is just another rock-solid configuration you'll see in plenty of rooms.
Now, let's talk about specialized environments. Enter the C-arm support system. The X-ray tube and the image receptor are literally mounted on opposite ends of this giant C-shaped arm. This setup is a total game changer for interventional radiology and surgical suites. Why? Because you need unbelievable flexibility to get real-time imaging from almost any angle, all without constantly having to shift the patient around on the table.
Okay, so here's a crucial point. When X-rays are actually born inside the tube, they don't just shoot straight down. They're emitted isotropically, which is just a fancy way of saying they fly out in literally every direction with equal intensity. But obviously, we only want the ones coming straight out of that special window, what we call the useful beam. And that's exactly why the protective housing is so genius. It physically guards against unnecessary exposure by absorbing all those stray, rogue X-rays. To put that into perspective, a properly built housing brings that leakage radiation way down to incredibly safe levels, specifically less than 1 milligray per hour at a distance of 1 meter. Plus, it's packed with oil to act as a thermal cushion and has these heavy-duty, high-voltage receptacles to make absolutely sure nobody gets an electric shock.
Deep down inside that protective housing is the enclosure, and its whole job is to maintain a perfect vacuum. You need that vacuum for efficient X-ray production. If a tube gets even slightly gassy, your X-ray production plummets and the heat generation just spikes out of control. Now, there are two main types of enclosures: glass, usually made of Pyrex to handle the insane heat, and metal. Modern high-capacity tubes, they almost exclusively favor metal. Here's why. As a glass tube ages, vaporized tungsten literally coats the inside of the glass. That messes with the electrical properties and causes arcing. Metal enclosures, on the other hand, maintain a completely constant electric potential, which totally prevents that arcing and gives you a much longer, way more reliable tube life.
All right, moving right along. Section 2, Internal Components. Let's look inside that vacuum tube.
Let's zoom way in on the cathode. This is the negative side of the X-ray tube, and it features a really clever dual filament design. It's essentially made of two parts, the filament and the focusing cup. See those two tiny coils of wire? Those are your filaments. They give you separate electron beams so you can create two different focal spots on the anode target. Usually you've got a smaller one, like 0.5 millimeters, for when you need super high, crisp resolution, and a larger one, like 1.5 millimeters, when you're running higher heat techniques.
But wait, how do we actually get the electrons out of those little wires? It happens through this vital phenomenon called thermionic emission. Sounds intense, right? Well, it is. When you pump a high current through that filament, it gets dramatically hot. That intense heat literally boils the outer shell electrons right off the tungsten atoms, creating this dense cloud of electrons that are just hovering there, waiting to be violently hurled toward the anode the second that high voltage hits.
Which brings us to Section 3, X-ray tube failure. Let's talk about the thermal characteristics and what happens when things break.
Look, the lifespan of this tube is, for the most part, right in your hands. When a tube tails, it almost always comes down to 3 main culprits, and they all revolve around heat. First, a single, massive, excessive exposure can cause localized melting, pitting, or literally crack the anode. Second, if you keep the tube at a super high temperature for a long exposure time, you're going to cause bearing damage in the rotor assembly. That leads to warping and awful friction. And third, even if you do everything perfectly right, the sheer extreme heat of normal use is going to cause tungsten vaporization.
Let's anchor that last one, tungsten vaporization, to something super relatable, the incandescent light bulb effect. The single most common cause of sudden, abrupt tube failure is electron arcing from the filament to the enclosure. And that happens because of that vaporized tungsten we just talked about, slowly coating the inside of the tube. It works exactly like an old-school light bulb. The more you use it, the more that little filament wire vaporizes. It gets thinner and thinner and thinner until, pop, it just snaps, leaving you with an open filament.
To give you a real sense of scale here, we don't measure tube life in hours like a standard light bulb. We measure it in tens of thousands of exposures. To put that into perspective, many modern CT X-ray tubes are guaranteed by the manufacturer for exactly 50,000 scans before this inevitable burnout happens. 50,000? That is a staggering amount of heat generation for one single component to handle over its lifetime.
Okay, final stretch. Section 4, rating charts. This is all about how we prevent that failure from happening.
You literally have the power to extend the lifespan of this equipment just by using the minimum radiographic factors necessary to get a good exam. To help you do that, we rely on 3 essential rating charts: the radiographic rating chart, the anode cooling chart, and the housing cooling chart. Now, I know what you're thinking. Doesn't the modern imaging system just do this for me? And yes, they do have these charts digitally embedded as microprocessor protection circuits, but it is absolutely crucial that you understand the why behind them, so you can check that the safety systems are actually working and manually gauge if it's safe to run back-to-back high-heat exposures.
So, what does this all mean for you? Well, you now know the anatomy of the tube, the insane physics behind thermionic emission, and the thermal breaking points of the equipment. You have the charts and you have the knowledge. The question is, will you be the technologist to protect the tube, maximizing its life for thousands of future patients, or will you be the one who burns it out? The choice, and honestly the responsibility, is completely yours. Keep shining bright, and I'll catch you in the next explainer.